So in this video, we're going to learn how to solve linear systems of equations on three variables with three equations. And we'll do this by example, and then we'll discuss what's going on. So we'll be using elimination. And what we're going to do first is we're going to go ahead and get rid of the x in both of these equations here. So we'll start with equation number 2. And let me go ahead and call this equation 1, equation 2, and equation 3. And what we want to do is we want to replace equation number 2 with equation number 2 minus equation number 1. So we're going to get x plus y minus z minus a x plus y plus z is equal to a negative 5 minus a negative 1. So let's simplify this first, and this is then going to become a x minus x is 0, y minus y is 0, and negative z minus z is a negative 2z. This is going to be equal to a negative 5 plus 1, which is negative 4. And we haven't changed anything with equation 1 or equation 2, so we'll rewrite these. So we'll get x plus y plus z is equal to a negative 1, and we'll also get a negative 2x plus 3y minus z is equal to 9. So now, again, we want to go ahead and get rid of this negative 2x using equation 1. And so we'll rewrite this as equation 3 is going to be equal to equation 3 plus 2 times equation 1. Therefore, we'll get a negative 2x plus 3y minus z plus 2 times x plus y plus z is equal to 9 plus a negative 2. Simplifying this, we see that this becomes a negative 2x plus 2x is 0. Then we'll get a 3y plus 2y is 5y. A negative z plus 2z gives us a positive z, and this is going to be equal to 7. So we'll rewrite our system. Again, this is going to become 5y plus z is equal to 7. Equation 2 hasn't changed. This is a negative 2z is equal to a negative 4. And equation 1 is still x plus y plus z is equal to a negative 1. And we can use this to solve our linear system now. So let's go ahead and start a new page. And the thing to notice is that we have this negative 2z is equal to 4, and this tells us that z is going to be equal to 2. So now that we have z is equal to 2, we're going to plug it into this equation here, and this tells us that 5y plus 2 is equal to 7. So minus 2 on both sides gives us 5, and then divide by 5 gives us that y is equal to 1. So we have our y, we have our z. We're going to plug this into equation number 1, and this says we'll have x plus 1 plus 2 is equal to a negative 1. Solving for x, this tells us that x is equal to a negative 4. So therefore, the solution to this linear system is going to be x is equal to a negative 4, y is equal to 1, z is equal to 2. And we can write this as a coordinate. This is going to be x, y, and z is equal to negative 4, 1, and 2. And this is our solution. So this method is known as elimination again. Another phrase for it is called Gaussian elimination, or the Gaussian algorithm. So let's go ahead and summarize what the goal is whenever we're using Gaussian elimination. To use Gaussian elimination, we always start with a linear system, such as this linear system here. And what we want to do is we want to use equation number 1 to eliminate the following terms in the equations beneath it. So once we use equation number 1 to get rid of these terms, we get a linear system of the following description. And notice in this new linear system, these constant values in front of our variables have changed. And now we're going to repeat the process. We're going to use this time equation 2 to get rid of this term here, and we'll get the resulting linear system. And again, notice that the variables in front are the variables in our third equation may have changed. And once we've reached this point, we can always solve this linear system by back substituting for our x3, then solving for our x2, and then solving for our x1. And I just realized that I had an extra term. In this system here, our equation 2 is of the following form. Now let's go ahead and look at an example where we have a linear system whose solution has an infinite number of solutions. And we want to solve the following system. Again, we'll just be using the Gaussian algorithm. And so what we're going to do is we want to get rid of this 2x and we want to get rid of this negative 4x. And again, we're going to replace equation number 2 with equation 2 minus 2 times equation number 1. So I'm going to skip all the computations that we did in the previous problem just to save us time. Nothing changes with equation 1. This is still just x plus 2y plus 5z is equal to 20. Nothing has yet occurred to equation number 3. This is going to be a negative 4x minus 6y plus 12z is equal to a negative 4. But now, again, we're replacing equation 2 with this information. So we'll get a 2x minus 2x, so we'll get a 0 here. Then we'll get a 3y minus 4y, so this becomes a negative y. Then we'll get a negative 6z minus 10z, so this becomes a negative 16z, which is going to be equal to 2 minus 40, which is negative 38. Now, we want to go ahead and get rid of this negative 4x here. So we're going to replace, again, equation number 3 with equation number 1 plus 4 times equation, this is equation 3 plus 4 times equation number 1. So nothing has changed to equation 1 or equation 2. Let's go ahead and rewrite them. But equation number 3 will now have a negative 4x plus 4x, so we'll get a 0 here. The second part will have a negative 6y plus an 8y, so this becomes a positive 2y. And then we'll get a 12z plus a 20z, so this becomes plus 32z. And this is going to be equal to a negative 4 plus 80. So this is going to be 76. And we're done with the first step of our algorithm. And now we're going to go ahead and use equation number 2 to get rid of this 2y here. So we're going to replace equation number 3 with equation 3 plus 2y. Again, nothing changes to equation 1. This is x plus y, 2y plus 5z is equal to 20. Equation 2 remains the same. We have a negative y minus 16z is equal to a negative 38. But then we'll get a 2y minus 2y, so this is going to be 0. And then we'll get a 32z minus 32z, so we'll get, again, minus 0. Then finally we'll get a 76 minus 76, so we'll get 0 here. And let me go ahead and copy this onto the next page. So rewriting this so that it's a little neater, this says that we'll have x plus 2y plus 5z is equal to 20. We have a negative y minus 16z is equal to a negative 38. And here we'll get 0 is equal to 0. And this is where it gets a little strange. What this is telling us is that two of the planes that we were looking at were actually the same plane. So 0 is equal to 0 is telling us that we have this free variable. Now, since the other two equations, we have x, y, and z are dependent on something, and we have y and z are dependent on something, but we don't have any real restraints on what our y, z, or x can be in equation number 3, then we have a free variable. So generally, when we don't have anything going on in equation 3, and we have x, y, and z represented in the other equations, then we say that z is equal to z. In equation number 2, what we can do then is we can write this in terms of z. So remember that the solution to a linear system is given by three ordered numbers, x, y, and z. And so we have that z can be equal to any number. And what equation number 2 and equation number 3 are going to allow us to do, it's going to allow us to find what our y and what our x have to be. So let's go ahead and look at equation number 2. This is negative y is equal to a negative 38 plus 16z. Or in other words, we get y has to be equal to a 38 minus 16z. So we'll rewrite our y as 38 minus 16z. And now that we know what our y has to be, we're going to go ahead and look at equation number 1 and plug in what our y has to be in terms of z. So let me go ahead and start a new page, and then we'll come back to this once we solve equation number 1. So let me plug this, or bring this equation with us. Again, we just found that y is equal to the following. So plugging in y for this here, we'll get x plus 2 times the 38 minus 16z plus 5z is equal to 20. And again, we just need to go ahead and solve for x. So simplifying this first, and we see x is equal to, x plus 76 minus 32z plus 5z is equal to 20. Therefore, we'll get x plus 76 minus 27z is equal to 20. So x is going to be equal to a negative 56 plus 27z. Therefore, the solution set for this is going to be infinite. And it's going to be given by these equations here.